So this is how basically our VNA display looks like, and you can see that right now I've just done a preset to this vector network analyzer. You can see that it's working from 70 kilohertz to 40 gigahertz. And just to let you know the options that are required for doing this demonstration, we will definitely need option 35, which is the digitizer board, which gives us the IF bandwidth going as high as 200 megahertz. Then we also need option 42, which is the PulseView option. So you can see that the unit that I have today is already equipped with all the options which are required. Now I've already done few setups, you know, because otherwise I'll take a lot of time to set up all those things. So I'm just recalling the setup here that I have, and basically what I've done is that, you know, this is a start frequency of 5 gigahertz, stop frequency of 15 gigahertz. The IF bandwidth is 1 megahertz, and I've switched on the averaging because pulse is something that you would want to make an average measurements of. I'm already in the pulse profile, so let me now go back, because this is the basic setting only. I mean, I've not done something which is like rocket science. So you just have to fix in the frequencies, you have to make sure that the powers are fine, and then you also have to make averaging on. I've kept an averaging factor of 10 here, and I'm doing it per sweep, and the IF bandwidth right now is 1 megahertz. But you will see that because we are already in the pulse mode, all the measurement channels are going through the widest IF that we have in place, so it's already 200 megahertz. Let's go to applications, and you can see that we have various options here, and as you add on keep on adding the options, you will get more and more options and results like that. Let me quickly go back to PulseView setup. So this is basically option 42, and it's called as PulseView setup. When I enter here, you can see that we have actually very beautiful wizard to actually control the entire pulse. And as I mentioned, we have 4 pulse generators. You can see that here is PG1, PG2, PG3 and PG4. These 4 pulse generators are basically at the backside of the VNA, and maybe at the end of the video I will show you the backside of the vector network analyzer as well. But what we have done is that we have connected PG4 from the backside of the VNA to the input port of the pulse generator, the pulse demonstration module. So that means signals coming from the pulse generator number 4 are going to act as a key to on and off the RF coming from the VNA port 1 and going into port 2. So as I said, yes, we have 4 pulse generators, then we have various measurements, and as I was telling you in my first presentation, that you can have a pulse profiling mode, you can have a point-in pulse, you can have a pulse to pulse. Then we do have some more interesting things, and this is not a part of this video, but if you guys are interested, I can do another session for you. So going back, let's first configure the pulse generator. What kind of pulses do we want? So first things first, we have to enable the pulse generator, and when I click on enable, you can see that the PG4 basically gives you a pulse as per the delay, which is 0 second here, and then the width of 1 microsecond, which is basically the width that you're seeing on this green signal here. First thing first, let me configure the PRI from 10 microseconds to 1 microsecond so that you guys can see very clearly what we are trying to do here. So I've just done a PRI of 1 microsecond. I'm trying to enable a singlet pulse, and the delay is 0 seconds, and then the width here is 1 microsecond. So that means the PRI and the width are the same, and that's why you see that these two channels, like the green one and the receiver profile, is exactly the same. Let me do this to say roughly around 200 nanoseconds, and as I do a 200 nanoseconds, you can see that this green pulse from the pulse generator number 4 has turned its shape. So you actually can see that how easy this is to set up. At the same time, if there is any confusion of what this PG4 is and what this is doing, normally people have this complaints that we should have something to name this pulse generator. So we have listened to our customer's requirement, and instead of this I can give it a name of, say, pulse modulation. Okay, I say an OK, and you can see that now instead of PGen4 I have renamed it to as pulse modulation. That means I'm using the pulse generator number 4 to act as pulse modulating for the pulse demonstration module. So I go there, and as I mentioned, as per the diagram of the pulse demonstration module, we have to keep in mind that PGen low is closed. So that means it has to have a low side. That's why having inverted polarity is important, otherwise the pulse modulation test set is not gonna work. So we have configured this. Now what we need to do is the rest of the things I will show you maybe later, but today I just wanted to show you that we can configure a number of pulses. First we have done a singlet, and now let's do the measurement that we have. Let's go into pulse profiling. So that means we want to see as to how this pulse is looking. So we have a receiver in place, and this feature in the next video I will be showing you why having independent receivers is a good option, because normally in the measurement world today there are not a lot of VNAs which can have independent receivers, because normally what happens is that, say suppose if you have a DUT which adds in a lot of delay, say in your pulse. So the reference which is going to the reference receiver of the VNA, when it is stored and when it goes to the B1 receiver, B2 receiver, then there is a time lag between the two, and if the two are not synced, then your S parameters are not going to show you the same thing. So sometimes when you have a delay line in between as a DUT, then it's good that if you have independent receivers in place, you can actually do a time sync between the two, and you can make sure that the measurements that you are doing are fine. That is a part of my third pulse demonstration video, so you can have a look at that. For that I will be using Anritsu's pulse modulator test set, which is basically SM6628, and that pulse modulator test set takes care of all the things for the modulation. If there are some extended applications wherein you need both modulation on the transmit and also on the receive side, then you can have various versions of this pulse modulator test set. Coming back to this, the measurement width, you can see that so this measurement pulse profile is the pink B2 profile top corner of the wizard for the pulse view. So the measurement width basically is how finely you can actually resolute this pulse. Now because Anritsu has this 200 megahertz of IF bandwidth, we can actually resolute a pulse to a scale of 2.5 nanoseconds. Now in my first video I told you the significance of having lower and lower pulse widths in the domain of radar applications. The lower your pulse width is, the more range you can actually go on and try to find your enemy aircraft or something like that, right? So that means this world of avionics and aerospace and defense is basically going towards narrowing their pulses more and more, but when they do that, they do need to verify those kind of narrow pulses. Today, up till today, in the measurement world, the best resolution that was available was roughly around 12.5 nanoseconds. Now with this 200 megahertz IF bandwidth receiver that we have, we can actually resolute the pulses as close as 2.5 nanoseconds. Right, so when I do that, apart from that, you can see that there is a small white arrow on the pink B2 profile. So that is basically the start of the B2 profile, start of the measurements of the B2 profile. And you can see that right now it's 2 microseconds at the stop, and we really don't want to do that, because that is that will actually, you know, get a lot of data which we don't require, because our pulse that we are trying to measure here is only of the order of 200 nanoseconds. So let's make this measurements to 400 nanoseconds. Now you can see that the white cursor, the second cursor, has come here. We can actually go lower than that, but I just wanted to show you how this actually looks. Now there is a very important point here, which is the number of points here, you know, and that is something that we want to have rightly in place just to avoid the aliasing. So when you divide 400 nanoseconds by 2.5, you reach a number of 160. And because we do not want any aliasing for safety reasons, let's just put it to 161 number of data points. Now once that is done, actually I have fixed on my pulse modulation, which is basically happening inside the demonstration module, but I'm using the PGen from the VectorStar to actually help do the pulse modulation. And for the measurement window also I have catered. So you can see actually this is pretty cool, you know. Why? Because you can actually visualize what pulse is gonna be coming and what measurement width you need to define here. And once I am done with the setup, what all I need to do is just click here and say done. Now what the VNA is gonna do is that they are gonna you know, configure the receiver, and you will see that you'll have the pulse here as is, and this is basically the pulse that is being now here is something that you will see that there is a lag here, although we started the pulse at 0 nanoseconds, but this lag is basically because of the switch which is inside the pulse demonstration module. And this pulse demonstration module, because of the switch, you know, it takes some time to switch on and then to switch off. That delay is because of that. So you can see, and we can put a marker, and it's roughly I believe around 35 nanoseconds. But again, that's not important. It's important how finely you can resolute the measurement. So what we are gonna do here is let's see if this was not 2.5, you know, we had an instrument, say suppose instead of 2.5 nanoseconds, it was having a resolution of say roughly around 12.5 nanoseconds. So what would have happened there is the fact that if I change this resolution to 12.5 nanoseconds, then of course the number of points are gonna be very low. It's gonna be 32, but again, just for aliasing, I put 33 here. And if I say done, then the pulse is gonna look something like this. So there are a lot of ringings or some major parameters, some major fluctuation in the pulse, which you may not be able to capture if you have a measurement width of say around 12.5 nanoseconds. So lower the measurement width, or the lower the resolution of the VNA that you have, the better you can actually see the profile of the entire pulse. Now if say suppose you had instead of 12.5, say suppose you had something like 20 nanoseconds. Okay, let's see what happens here. So if I do 20 nanoseconds, it's going to be roughly 21 points. So let me just quickly do that, and let's see. So you'll see that glitch which was there in the pulse initially, with the with a poorer resolution, you will not be able to see any sort of glitches which are happening in your pulse. So coming back to 2.5 nanoseconds in 400, I do it to 161. You can see that now we have a pulse which is pretty good in shape, right? So that means now you can now with this simple thing you can do a lot of stuff, because we have markers and you can put it on wherever you want. You can see the PRIs, the pulse width, the pulse repetition frequencies, the overshoots or the ringing. So 2.5 nanoseconds of resolutions gives you a lot. Now this module we actually wanted to test on 10 gigahertz. So when I do that to 10 gigahertz, you'll see that this is basically how it actually should look, you know, because this module is being configured like that so that we can show to our customers that this is the resolution that they will get every time, you know. And again, if I go back to the pulse setup, and instead of 2.5 I did it to 12.5 nanoseconds, and the number of points be 33, you'll see that you're gonna miss some events which you now with Enritsu VNA you will not be able to miss. So you can see that the resolution is something which is very, very important, and that's why Enritsu has the leadership here. So I go back to my setup, I do a 2.5 nanoseconds and I do a 161 number of points, and now I can see all the ringings which are there in my pulse demonstration module. So this was one setup. Let me go back again to pulse view configuration, and now instead of a singlet I actually want to have a doublet. That means I want to have two pulses. Now you can see that this was the first pulse was 0 seconds, and then the width was 200 nanosecond. Let me do this to say 350 nanoseconds, and the pulse width maybe say 500 nanoseconds. Right, so now you can see that I have two pulses here. They are still inverted polarity, but now because my measurement is only up to here, I may not be able to see the second pulse. So what I need to do is, instead of 400 nanoseconds, I have to do this to say 900 nanoseconds, and you can see that now the two white notches on the B2 profile are actually covering both the pulses. Now the good thing about this wizard is the fact that you can actually play with the cursor, the measurement bandwidth for the B2, which is the receiver side of the VNA. You can actually play with it, and whenever you see that, okay, now my two pulses are being covered, you can stop at that point and you say, okay, now I'm good to do the measurements. This kind of wizard is basically not available with anybody else right now in the industry. So I've done that. Now let's go back, just quickly check that okay, we have doublet. And just to let you know, because sometimes people say I really don't understand what's the meaning of delay. In fact, you can actually see it from the graphical wizard there on the top, but sometimes people say I'm a little confused. So for them, what we have done is we have explained what's the meaning of a quad burst thing. So a quad burst basically, so this is our starting point, which is the reference here. You can see you can compare it to the pink trace here. The delay is basically the first pulse that you have. So this is the delay, and this is the width of the first pulse. The second entry that you do is again starting from the same reference point. That is delay number 2, and then you have width number 2. So this is how it is configured. Let me quickly show you how this basically looks like. So I press on done, and now instead of one pulse we should be seeing two pulses. But as you can see on the right hand side, we cannot see it because there was this delay of initially 15 nanoseconds because of the pulse module or the demonstration module. So we have to take care of that as well. We go back here, and instead of the measurement stopping at 880 nanosecond, let's do a 1 microsecond, or maybe say 995 nanoseconds. So that we are covering the entire thing, or maybe you can actually reduce it a little, and let's say, okay, now this should be good enough. Yep, and I say done. Although I should have calculated the number of points, but it's just to show you that how quickly and how easily you can actually configure the pulse modulation using our not the same thing are actually applied when you have a pulse modulator test set. The only difference between a pulse modulator test set is the fact that the reference that the A1 receiver, which is the first reference receiver that we have on the VNA from the source side, so that reference will be also a pulsed one. In this particular demonstration where we are doing using the pulse demonstration module, the A1 receiver is still getting a CW. That's why, because it's easier. But if you need to have pulse modulator test set in place to give you pulse to have a RF pulsing, or say DC or IV pulsing, you can still use the pulse modulator test set, which I will show you in my next video. So this was for the doublet. Just like that, you can also do a triplet. And now, because we will have 3 pulses, let me quickly do some changes. So first pulse I want to make to 100 nanoseconds. The second one I can start with actually 200 nanoseconds and stop at maybe again 100 nanoseconds of pulse width, right? And the third one, because this is not 200, 300, so let's do a 350 nanoseconds, and then we say, okay, even for this pulse I need 100 nanoseconds of pulse width. So you saw that this red exclamation mark actually went off, and now you can see what are the pulses that you are generating using the pulse generator, and the modulation is happening actually at the demonstration module, right? So now if you want to play with them, because right now you have 3 pulses and your measurement is on the higher side, because we changed that, you can actually do some increments. So you'll see that, even in the graphical thing, you'll see that, oh wow, you can actually visualize what you're trying to do, and if there is something which is not working out for the measurement, it'll actually give you an exclamation mark. So let me do some measurements, and I really don't like putting into fixed numbers. I really like the way that you can actually see the pulses, and at the end of the day you would want ease of measurement, right? So now that we have 1, 2 and 3 pulses in place, and I'm just leaving the measurement window as is, so that should be easy. So I put done, and you should be able to see these 3 pulses very easily on your display. So again, this is to show you how easily you can actually generate pulses and provide modulation as well through this small demonstration module. It's the same principle with the pulse modulator test set from Android as well. The last one that I wanted to this was triplet. You could also have a quadruplet, and again, quadruplet will basically be the same, but let me quickly show you a few things. Okay, so I want to do, so let's change few things again here. 100 nanoseconds. Okay, this is 200 nanoseconds. I change this to 100 nanoseconds again, and this time I do it to 350 nanoseconds. I'm just quickly doing few things just to show you how easy and simple it is once you know how to configure things, right? So I have 500 nanoseconds, and again 100 nanoseconds of the width for my pulse, and you can see that now I have 1, 2, 3 and 4 on the green pulse modulation, and now I can start playing with the widths if you want. It's easier to play with the last one, because if there is any overlapping that you have, so you will have an exclamation mark. But let me now this time show you a few things which will actually tell you the capabilities that you can have. Okay. just doing it like that so that I can have smaller pulses as well. And for this one, I can have maybe a lower as well. Now what I'm trying to do here is have you show different pulses of different width, and rest of the things I'm leaving the same because my measurement window hasn't changed. I'm just playing within that same measurement window, so you can see that 1, 2, 3, 4 U. Now the second one is not looking very good because there is a little bit of overlapping here, and again because this is a demonstration module which will have its own thing, but you know, the story is that you can easily, very visually, you can do all the measurement. The last measurement or the last generation of the pulses that I want to show is basically the burst, and with that I've actually changed the setup to actually 10 microseconds as the PRI, and you can see that the number of bursts that I've chosen is 9. Now burst is actually very important, especially for the people who are doing a lot of radar work. They are sometimes very interested to know if a chirp signal happens, and you know, they actually want to see if I send in a bursty signal, what's going to happen, or a burst profile if I'm going to send to my radar, what's going to happen. So for testing these TR modules, they actually send in the burst, and this is very important, again coming from some of our customers, that burst is a good feature to have. So the number of bursts can be defined. Right now I defined it to 10, but you can actually make it to 8, and you can see that as you keep on deleting the number of bursts, you can graphically see that what we are doing here. So you have 9 bursts, and the period of each pulse is actually 1 microsecond. If I keep on increasing, because 2 into 9 is 18 microsecond, but the entire PRI is 10 microsecond, that's why I'm getting this error. But if I do it to 1, that means there are 9 pulses, 1 microsecond each, that means still fitting the PRI of 10 microseconds. I'm not adding any delay here, and the width is 200 nanoseconds. I can actually play with a little with the pulse width, but not much, because if it you know, coincided with others, then it's gonna be a problem. And on the measurement side, again I've configured the B2 receiver. Again, same thing, measurement width of 2.5 nanoseconds. The stop is 9.8. because this pink extreme right end cursor, that's my measurement window, and if you divide 9.8 microseconds by 2.5, you get a number of 3800, and you add in one more point. So once that is done, I click done here. Now it's gonna take some time in processing, because for each and every pulse it's you know, trying to process the data. This graph that you're seeing right now was done before, but whenever an update happens, that is the time you will be able to see the pulses as is. So this display right now is freezed. It's an older display because I was doing some settings, but you will see now this one has updated right now. So this is the first of the averaging. So that means now you can actually see 9 pulses with entire, the overshoots, the ringing, and entire pulse in the complete manner. So as you saw in the pulse window, we have 4 pulse generators. Again, you can configure each and every one as different. You can have singlet, doublet, and even these names here for PG3, you can change it to say having a doublet one or a triplet one, you know. And then the measurement with us is very, very simple to use. In my next video, I will show you the point in pulse measurement, and I'm looking forward for you guys to come back and join this video as well. Thank you so much for listening in, and this session will keep on going right till the end until we cover all the applications.